Welcome to BuildingsOne video series. Whether your facility is a 50,000 square foot mixed-use center or a 1 million square foot office building, the facility manager's practical application of the HVAC Optimum Start concept offers a clear opportunity for energy conservation. Added benefits include control of operating expenses and reduction of the building's carbon footprint. Optimum Start concepts were introduced to the HVAC and building automation system (BAS) industry over 20 years ago with some success. Despite advancements in BAS controls and new software technology, including artificial intelligence and machine learning, Optimum Start can be consistently implemented with a fundamental understanding of tenant HVAC lease terms, building thermal recovery concepts, HVAC equipment capacity, and a few basic BAS control commands. By reviewing these concepts and illustrating a basic Optimum Start simulation, this video will demystify the overcomplicated and inconsistent programming solutions being promoted in the BAS industry. The Optimum Start solution should emphasize three basic criteria: desired indoor temperature set point when cooling and when heating. They should be different values for each operation. The building's occupied period begin time, otherwise defined in the landlord-tenant lease as the time HVAC service begins during weekday business hours, and building indoor temperature recovery time, verified by monitoring indoor temperatures prior to and at the occupied period begin time. Unoccupied period setback temperatures and other energy conservation measures, such as exterior shading and closing perimeter blinds, will impact building indoor temperature recovery time. While ASHRAE Standard 55, Thermal Environmental Conditions for Human Occupancy, recommends a liberal range of indoor temperatures ranging from high 60s to high 70s degrees Fahrenheit, commercial leases generally stipulate a range of 70 degrees Fahrenheit heating season to 74 degrees Fahrenheit cooling season, plus or minus 2 degrees. The facility manager's measured approach in programming indoor temperatures at the lower end of the humid comfort zone during heating season and at the higher end range during cooling season will reduce building energy consumption. The following rationale validates establishing distinct indoor temperature heating and cooling set points. This operating practice requires significantly less mechanical and thermal energy to cool and heat the building and is advised by leading HVAC industry and environmental organizations. When occupants enter a facility, the relative difference between outdoor temperature and indoor temperature will be less extreme, supporting an acceptable comfort transition, and during the spring and fall transition season, early morning warm-up sequence, adding heat to achieve a mid or high temperature range of the comfort zone leads to overheating the building, resulting in mechanical cooling earlier in the day than would be needed otherwise. With these factors as a background, our Optimum Start simulation will be based on indoor temperature set points of 70 degrees Fahrenheit during heating operation and 74 degrees Fahrenheit during cooling operation. Most commercial office leases stipulate HVAC services 10 hours per day, Monday through Friday, typically 8 a.m. to 6 p.m., and in some cases 7 a.m. to 5 p.m. From an energy controls perspective, the period of mandatory HVAC services is referred to as occupied period or occupied mode. To provide human comfort conditions outlined in the landlord-tenant lease, building operators must start HVAC systems at or prior to the occupied period begin time. For our Optimum Start simulation, we'll define the occupied period begin time as 8 a.m. Monday through Friday. During the building's unoccupied period, typically 118 hours per week during nights and weekends, when HVAC services are not compelled by the lease, BAS controls automatically shut down HVAC equipment to reduce energy consumption. This is known as time of use scheduling, a practice much like programming a residential smart thermostat. Time of use scheduling allows indoor temperatures to drift outside the building's occupied period temperature comfort range. During the unoccupied period, BAS controls normally cycle on HVAC equipment when indoor temperatures drift too high during the summer cooling season or too low during the winter heating season. When indoor temperatures return within the prescribed unoccupied temperature range, HVAC equipment will cycle off to continue the energy reduction process. Establishing unoccupied setback temperatures too close to the occupied period temperature range will lead to excessive HVAC system operation, wasting electricity and thermal energy. Cooling and heating mode unoccupied temperature set point is referred to as unoccupied period setback or nighttime setback. A common unoccupied period indoor temperature setback is 60 degrees Fahrenheit heating mode and 82 degrees Fahrenheit cooling mode. Here is a basic office building BAS control strategy for heating operation, illustrating indoor air temperature set points during the occupied and unoccupied periods. Note the 70 degrees Fahrenheit occupied period set point and 60 degrees Fahrenheit setback during the unoccupied period. And here is a basic BAS control strategy for cooling operation. Note the 74 degrees Fahrenheit occupied period set point and 82 degrees Fahrenheit setback during the unoccupied period. Structured BAS programming and automated control of HVAC equipment is referred to as sequence of operation. A specific sequence of operation is developed for various operating criteria, including occupied and unoccupied cooling, occupied and unoccupied heating, and optimum start. During each unique sequence of operation, the BAS monitors specific data, including time of day, outdoor and indoor air temperatures, and HVAC system temperatures, to maintain desired indoor occupant comfort conditions in an energy-efficient manner. With our BAS program setting the building occupancy time of 8 a.m., indoor temperature heating set point of 70 degrees Fahrenheit, and indoor temperature cooling set point of 74 degrees Fahrenheit, the next step is to program our BAS Optimum Start simulation based on what is referred to as estimated recovery time, then observing and readjusting as necessary. By definition, optimum start time is the latest time the HVAC system should start so that building indoor temperatures reach the desired set point at the occupancy begin time. Optimum start time is directly correlated with recovery time, the time required for the building's HVAC system to remove internal heat during the cooling mode or to add heat during the heating mode. Facility managers having a basic understanding of building thermal recovery concepts are better equipped to ensure that BAS enables an optimum HVAC start time. While some building operators consider shutting down HVAC equipment prior to the end of the lease-defined occupied period, generally described as coasting, there is less energy reduction opportunities in implementing optimum stop time at most facilities. Operation of HVAC systems through the entire lease-defined service period is primarily driven by a fresh air requirement provided by the building's air handling equipment. Conversely, to the extent building operators can optimize HVAC start time such that indoor temperatures reach the thermal comfort zone at the beginning of the occupied period begin time, but not earlier, building owners and tenants benefit from reduced energy consumption. In most U.S. geographical regions, owner-operators closely monitoring building thermal conditions will note during 4 to 6 months of the year, indoor building temperatures are within the occupied comfort zone range without starting HVAC systems prior to occupancy begin time. Overcomplicated optimum start programs that monitor up to 100 data points almost always start HVAC equipment too early, often several hours before necessary. The recommended optimum start solution is one that is easily understood and can be monitored and adjusted by the facilities management and operations team. An optimum start sequence that incorporates basic data points limited to least defined occupied period begin time, desired occupied period indoor temperature set point, and actual indoor temperatures polled by a temperature sensor during the optimum start period will ensure an effective HVAC start and energy reduction solution. A well-placed indoor temperature zone sensor or several zone sensors will transmit BAS input data required to determine optimum HVAC start time to reach desired indoor temperatures at the occupied period begin time. To ensure tenant comfort in all areas of the building, an effective zone sensor strategy will start HVAC systems based on sensor temperatures having the greatest differential from the desired occupied temperature set point. For example, during summer season, BAS input could be from a sensor on the west side of the building to factor solar heat gain from the previous day after HVAC system shutdown, or the sensor could be on the east side of the building to account for solar heat gain incurred during early morning prior to startup.
Why not look at outdoor temperature when considering optimum start time?
That's a great question. While many BAS control companies appropriately utilize outdoor temperature data in operating HVAC systems, as it relates specifically to optimum start, outdoor temperature is much less relevant and tends to complicate reliability and consistency in optimum start programs. Practically speaking, early morning indoor temperatures are an accumulation of previous night or weekend outdoor weather conditions, the predominant factor attributable to building internal heat gain or heat loss during the unoccupied period. So prior to optimum start, if a building's indoor zone temperature is 80 degrees, HVAC mechanical cooling is required at, let's say, 5:30 a.m. to reach desired comfort zone temperatures by occupied period begin time, regardless if outdoor air temperatures are 60 degrees or 70 degrees. In another example, during the spring or fall season, if a building's indoor zone temperatures are within the desired comfort zone prior to the occupancy begin period, why early start HVAC systems just because outdoor air temperature is 50 degrees or even 40 degrees? Humans breathe in oxygen and exhale carbon dioxide as a natural part of the breathing process. Outdoor fresh air is required during the occupied period to maintain acceptable CO2 levels in the building. If building HVAC systems fail to adequately introduce fresh air into the building, CO2 levels can increase, resulting in potential occupant health issues. However, during most unoccupied morning warm-up or cool-down cycles, fresh air is not required, and if introduced into the building, typically results in increased energy consumption. By monitoring outdoor air conditions, the BAS can control and close fresh air dampers during the morning warm-up and cool-down cycle. For buildings having limited fresh air damper control options, it's not uncommon to see fresh air dampers fixed at a predetermined minimum position during startup. Alternatively, during certain cooling season unoccupied periods, for example, a summer weekend night, tactical cycling of building air handling units to bring in relatively cool outdoor air while exhausting the building's warm air at off-peak electricity rates will shorten the recovery time and energy demand on Monday morning. Larger buildings having significant investment in BAS controls might consider enthalpy, a measure of humidity and energy content in the air, to establish the most energy efficient HVAC system sequence of operation and optimum start. However, this should be closely reviewed so that it is proven to be an effective energy reduction strategy. In low-rise building applications, because self-contained rooftop AC units are often not fully integrated into a central HVAC system sequence of operation, control of RTU start times and fresh air damper operation is often overlooked. Rooftop AC units and associated dampers and controls are often configured with pre-programmed default controls. In some cases, the unit may have basic control points that need to be configured during or after installation. Similar to large building central HVAC systems, introduction of fresh air during the optimum start cycle typically increases recovery time and energy consumption. Okay, at this point in the video, it's time for us to set up an optimum start schedule for cooling operation and then for heating. Let's assume our building is 200,000 square feet or greater with a central HVAC system. From experience, we can estimate a cooling operation recovery time of approximately 1 degree Fahrenheit per 30-minute period. In other words, prior to the occupancy period, when the central HVAC chiller plant starts, it should take an estimated 30 minutes to decrease indoor air temperature 1 degree Fahrenheit. If you recall, our occupied period starts at 8 a.m. with a cooling comfort zone set point of 74 degrees Fahrenheit. Our unoccupied period indoor temperature reset is 82 degrees Fahrenheit. So, the maximum indoor temperature range from unoccupied to occupied begin time is 8 degrees Fahrenheit, calculated as 82 degrees minus 74 degrees. This establishes a maximum estimated recovery time of 4 hours, comprised of 30 minutes per degree decrease times 8 degrees. With that said, the earliest we would need to start the HVAC systems is 4 a.m., 4 hours prior to our occupancy begin time of 8 a.m. That's it. We've established our optimum start schedule that can be implemented in the building's BAS. The next step is BAS contractor input into the BAS system with a very basic schedule. For cooling mode, this is accomplished with a greater than formula applied to indoor temperatures during the recovery period range. So how does this work? As we approach the optimum start period, the BAS will pull a designated indoor temperature zone sensor, let's say every 15 minutes, starting at 4 a.m. At 4 a.m., if the indoor air temperature is greater than 82 degrees, the central HVAC plant will start in order to cool the building. If the indoor temperature is less than 82 degrees, then the plant will stand by, ready to start when needed. Through observation of actual indoor temperatures at the occupancy begin time, the schedule can be adjusted up or down, resulting in a consistent just-in-time start of HVAC equipment. By going through a very similar process, we can establish an optimum start schedule for heating mode of operation. From experience, we can estimate our heating operation recovery time is an estimated 1 degree per 20-minute period. In other words, prior to the occupancy period, when the central heating plant starts, it will take an estimated 20 minutes to increase indoor air temperature 1 degree Fahrenheit. If you recall, our heating comfort zone set point is 70 degrees Fahrenheit, and our unoccupied period indoor temperature reset is 60 degrees Fahrenheit. So the indoor temperature maximum range from unoccupied mode to occupied begin time is 10 degrees Fahrenheit. This establishes a maximum estimated recovery time of 3 hours, calculated as 20 minutes per degree Fahrenheit decrease times 10 degrees. With that said, the earliest HVAC systems would need to start is 4:40 a.m. to reach our occupied temperature of 70 degrees Fahrenheit by 8 a.m. For heating mode, this is accomplished with a less than formula applied to indoor temperatures during the recovery period range. As we approach the optimum start period, the BAS will pull a designated indoor temperature zone sensor, let's say every 20 minutes, starting at 4:40 a.m. At 4:40 a.m., If indoor temperature is less than 60 degrees, the central heating plant will start to heat the building. If the indoor temperature is greater than 60 degrees, the plant will stand by, ready to start when needed. Recovery time and duration of HVAC equipment operation and related electricity and thermal consumption is directly related to the HVAC load during the morning cool-down cycle. Successful optimum start cooling strategies fully load HVAC equipment to remove heat faster, achieving the shortest recovery time. This practice will result in less energy consumed over a shorter period of time.
What about spikes in HVAC equipment electricity and the utility company's kilowatt demand penalty charge? Wouldn't the kilowatt demand and overall energy consumption be less if we slowly ramped up the HVAC equipment load over an extended period?
That's a very good question. The answer is no, because electricity rates are more favorable during early morning hours. Also, a building's peak kilowatt electricity demand is almost always set later in the afternoon when additional occupancy-related electrical loads, for example lights, plugs, and elevators, is added to the HVAC system electrical load. There are limited exceptions, such as early morning electricity demand during very cold weather conditions in an all-electric building. This graph illustrates a typical cooling mode electricity demand curve at a building having an effective optimum start. The steep incline in electricity demand reflects a substantial and compact HVAC system kilowatt load, resulting in faster recovery time and overall less electricity consumption. You can see the pre-occupancy indoor temperature was 79 degrees Fahrenheit when the central chiller plant started at 5:45 a.m. The recovery time was 2 hours and 15 minutes, and the indoor temperature cooled to the established 74 degrees Fahrenheit set point at occupancy period begin time, but not much earlier. Later in the day, additional occupancy-related electrical loads set the peak electrical demand at 1400 kW. By monitoring indoor temperature at 8 a.m., we can adjust our scheduled start time earlier or later to reach desired set point at occupancy begin time. This graph depicts excess energy consumption related to overheating and cooling a building during the fall transition season. This is very common at buildings not having an effective BAS Optimum Start program. At 5:45 a.m., the heating plant started too early. Perhaps the BAS was looking at outdoor temperatures, which are relatively cool in transition seasons prior to dawn. The heating plant started and increased indoor temperatures to 75 degrees Fahrenheit, rather than 70 degrees Fahrenheit, the lower end of the comfort range. When outdoor temperatures continue to increase during the day, very common in the fall and spring, mechanical cooling was required as early as 11:30 a.m. in order to control indoor temperature and prevent overheating the building. If pre-occupancy heating was delayed and indoor temperatures were set at the lower end of the comfort zone, the building would have reduced both heating and cooling energy. In summary, a building's HVAC Optimum Start program should emphasize 3 basic criteria: desired indoor temperature set point when cooling and when heating. They should be different values for each operation. The building's occupied period begin time, otherwise defined in the landlord-tenant lease as the time HVAC service begins during weekday business hours, and building indoor temperature recovery time, verified by monitoring indoor temperatures prior to and at the occupied period begin time. On behalf of BuildingsOne, thank you for your interest in this video and your commitment to excellence in the facilities profession.